Section 3.2 is titled Exponential and Logistic Modeling. It's going to be very similar to what we did in Section 3.1, is we're going to be looking at the same two types of functions, both exponential and logistic functions, and using them to model and solve real-world application type problems. So this is actually just almost like even a continuation of Section 3.1's lesson. We'll begin this lesson with looking at the exponential population model. I could write it to be P of t equals P naught times the quantity 1 plus or minus r raised to the t power. This is used whenever population is growing or decaying at a constant rate. In this particular model, the P naught, is the initial population, and the R, I could say, is the constant rate of growth or decay. I might even add here as a decimal. So if it was 50%, you wouldn't put 50 right here, you'd put 0.5 right here. It's a very similar model. If you recall what we were working on in Section 3.1, in Section 3.1 we had said an exponential function was y equals a times b raised to the x, where the a was the initial value. Well, here we're calling P naught the initial population, but that's still in the same spot here of the function. And the b was the base being what was being raised to the power. Here the base is this quantity 1 plus r or 1 minus r. So really it's the same model, just kind of broken up and maybe redefined these variables to kind of fit what we're going to be talking about today. In this slide, we're asked to tell whether the following population models show growth or decay and to give the constant percentage rate of growth or decay. So we've got two cities. One is Happyville, and here's the function that models their population. The other one is called Sorrowtown. Here's what models their population. You might have an idea maybe already why one is called Happyville and the other one Sorrowtown as it relates to growth and decay. Well, so let's talk about Happyville first. I would say that Happyville represents exponential growth. Okay, why does it represent exponential growth? Well, it represents exponential growth because the base here, the base is greater than 1. If it's greater than 1, well, that means as time is increasing, this population is increasing every time we have a base that's bigger than 1. Well, so what is its constant percentage rate of growth? Well, if you go back to that last slide, that population model, the base, this number here, was 1 plus or minus r. Well, in our case, we're dealing with a 1 plus r because our number is larger than 1. So the question is, what was r? So that 1 plus r was equal to this number right here. And the answer would be, we would have 1 plus 0.0213. So that is the r. Well, if that's the r, then what's the percentage growth rate? If we convert that decimal into a percent, our growth rate percentage is 2.13%. Okay. If we look at Sorrowtown, well, they're sorrowful in Sorrowtown because their population is decaying. Their population model represents exponential decay, and we know it's exponential decay because their base right here is less than 1. In other words, from the 1 plus or minus r, this number was found by doing 1 minus r. So the 1 is getting smaller, therefore we've got exponential decay happening. So again, same question. as we had posed previous in the exponential growth problem, 1 minus what number, so 1 minus what gives us this 0.9894. And if you're unsure about the mental math, sometimes maybe a little harder in this instance, let's just write it as an equation. If we did 1 minus r and set it equal to 0.9894 and actually solve that equation for r, we'd subtract 1 from both sides. So negative r is equal to, that would be negative 0.0106. We can divide by negative 1, etc., so that we get r equals 0.0106. So that's the r as a decimal. So convert that decimal to a percent. We could say it's decaying at a rate of 1.06%. Well, let's use this population model to model bacteria growth as a common application. So it says, suppose a culture of 200 bacteria are put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 250,000. So I'm going to begin with this population model. And we need to figure out two values. We need to figure out what's the p sub 0, what's the r, and then which of the plus or minus are we going to use to complete this model. Okay, so the p sub 0, that's our initial population. Well, we started with a culture of 200 bacteria. Now for the plus and minus, we need to choose. We're going to choose plus if this represents exponential growth, and we're going to choose minus if it represents exponential decay. Well, our bacteria are doubling every hour, so they're increasing the number. We're going to choose plus. And then the percentage rate. What percentage rate would represent doubling? So if we go from 200 to 400, and 400 to 800, and 800 to 1600, what percentage are we increasing? And the answer is the percentage is 100%. So our r as a decimal, 100% as a decimal is 1 raised to the t. I might further just kind of finish writing this. More often seen like that. Okay, so there is our population model. Okay, that's the function that's going to model how many bacteria, what's the population of bacteria at any instant in time. So we put some number in for t, it tells us how many bacteria that there are. Now the question that we actually want to answer is when, not how many, but when will the number of bacteria be 250,000? So we want the population p to be 250,000 and we need to solve that for t. Okay. Well, in order to solve that for t, it requires some mathematics that we haven't quite studied yet this chapter, but we can use our graphing calculators to solve this problem, similar to how we did in the last section. So let me show how I'm going to do this. On the y equals screen on my calculator, I'm going to type in 200 times 2 raised to the x. The x can be t, so that's one function, and then the other one is simply 250,000. Okay, now I need to go into my window and adjust my windows. My x in this case is time, so I'm going to set my time maybe 0 to 20. That's partly just a guess. I know that I'm doubling, so 200, 400, 800, 1600. The numbers are getting fairly large fairly quickly, so I don't think I need to go too far out on the x-axis. The y values here, the min and the maximum y values, need to be the number of bacteria. Well, the number of bacteria begins at 200, so I'm just going to go a little lower than 200, say 0. And I'm going to need to end at 250,000, so I need a rather large y maximum. Maybe I choose 300,000 for the y maximum. And let's see if we can see this. We should see our exponential curve first, and then we should see a horizontal line at 250,000. And now what we want to figure out is the intersection point of these two lines. So second, and we're going to do intersect, move that up there, get as close as we can, and it's the x value that we're looking at, so there we go, about 10.3. Let's round there to 10.3. So we could say about 10.3 hours. Next problem, we're going to look at modeling radioactive decay, another common application of this population model. Suppose the half-life of a certain radioactive substance is 24 days and there are 10 grams present initially. Find the time when there will be 2 grams of the substance remaining. So let's begin again with this population model. P of t equals P naught times 1 plus or minus r raised to the t. And again, what do we need to know? We need 3 things really. We need to know the initial value, the growth or decay rate, and then we need to choose the plus or the minus sign to complete this model. So we have P of t equals initial population, or the initial amount. It tells us there are 10 grams present initially. So 10 times 1. We're going to choose plus or minus. Here the radioactive substance is decaying because it's a half-life problem. So there's half of the amount remaining every 24 days. So the amount is getting less, so we're going to choose minus. And if we have half left after every 24 days, that percentage rate is 50%. So 0.5 raised to the t. And if I simplify this, we have 10 times 0.5 raised to the t. Okay, so that is, again, our mathematical model that we can use to solve this particular problem. Now I want to know time in which there'll be 2 grams of the substance remaining. So we're going to put 2 in for the population, or the amount. 10 times 0.5 raised to the t. Now let's go ahead and graph this just like we did the last one and see if we can solve it the same way. So I'm going to type into one of the y1s is going to be 10 times 2, not 2, 10 times 0.5 raised to the x. The other one is 2. I am going to adjust my windows. 0 to 20. Yeah, I don't really know what to pick here, so let's just leave it at 0 to 20 and we'll just see if that's enough. For the y's, I'm going to go say a y minimum of 0 because this amount's decaying. We're not going to have a negative amount. And for the y maximum, I'm just going to call it maybe 12, as I just want to go a little bit bigger than the 10 right here. Okay, so there it is. We can see the intersection point. What I'm going to do, since there's so much empty space out here that's really unneeded, I'm just going to go back into my window. Maybe I change this x maximum to, say, 8, just something smaller. Okay, so maybe we can see this a little bit better. Okay, so there's my exponential model. You can see it's definitely decaying. And then there's my line at 2. So let's calculate the intersection point. And so there's my answer, 2.32. Okay. So we can say t is 2.32. Now let's think about units here. Like what did we just actually find? If half of this 10 grams is present every 24 days, well, then that means after 24 days there would have been 5 grams left. And after another 24 days, there would have been 2.5. You see what's happening is we started with 10, and then half of that is 5, half of that's 2.5, half of that's 1.25. So this is here like my amount. And what I've got here, this is every 24 days, right? 24 day, or actually that's 0 days, but then 24 days, we have 5 left. Another 24 days, we have 2.5 left. Another 24 days, we have this much left. So what's the units here? Certainly it's not after 2.32 days, we have 2 grams left. This is 2.32, I'm going to say half-life cycles, okay? But that's really not good enough. I'd really like my answer in days, since the unit in the problem was given to me in days. Well, there's 2 ways that I can fix this, and I'll show you both ways. One way is just simply to take my number that I have here and times it by 24. If I take 2.32 times 24, we end up with, put the answer here, 55.68 days. Now that kind of makes sense, that like 55 days right here, that we might have 2 grams left over. Okay. The other way to fix it would be this. In my population model that I wrote right here, I can actually adjust the power. Instead of t, I can adjust the power to offset by that 24 days so that I can include this times by 24 just right up in here. And I can do it like this, t divided by 24. What that's going to do on my graph, that's actually going to extend my graph out so that instead of seeing them intersect here at 2 point something, they're going to intersect way out here at 55 days. So that'll already be computed into the work in the model and into the graph right there. So just a couple ways you can do it. I was just showing it like this maybe to be consistent with what we have done. This is probably the more correct answer as far as setting up the model. We'd actually want to include that half-life up there in the exponent of this model. Next problem is one from our textbook. It says use the 1950 to 2000 data in the table 3.12 and the exponential regression to predict Phoenix's population for 2003. Compare the result with the listed value for 2003. So this problem we're looking at Phoenix, so we're not going to use Los Angeles at all, so I'm just going to get rid of that. And I'm actually, just in the interest of time, I'm not going to repeat the steps using this data. So we're just going to do the first part of this problem. So I'm going to begin by entering this data into my calculator, into the stat mode of the calculator, the stat feature. So I'm using the stat button right here, and I'm going to edit. And I've already typed them in, but let me just kind of explain what I've typed in. What you see over here are not the years. You see much smaller numbers. What I've done is I've just said that the year 1950 is year 0. And then 1960 is year 10 because it's 10 years from 1950. And then 1970 is year 20, and this is 30 and 40 and 50. So that kind of explains these values that you see in list 1. And then list 2, of course, that's just the population of Phoenix numbers corresponding to the correct years. Now what I want to do is the exponential regression. So here's how I do that. I go back into stat button, and this time I go across the top to calculate. And there's all these different regression models, and the problem is asking us to do an exponential regression, which is that one right there at the bottom. So I'm going to tell it that yes, the x's are in list 1, the y's are in list 2. I'm going to come down here to calculate and hit enter, and it's going to compute the model for me. Okay, so those numbers, and it even tells me how to arrange them. A times b raised to the x, and these are the numbers I'm going to use for a and for b. So let's write that down on the paper here. So the model is y equals 185.07 times 1.045 raised to the x. If you prefer, you could call this P of t equals 185.07 times 1.045 raised to the t. Now, if you want to make it look like a population function and what we've been writing on the previous problems, you could certainly rewrite it to look like that. So what we want to do now is use this model to predict the population of Phoenix in this year right here, 2003. And 2003 would be represented by a t-value of 53. It's 53 years from 1950. So we want to find P of 53. So this is all calculator work. We just need to type this in, work it out. When I do that, I get P of 53 equals 1,907.7. Well, let's compare that to the actual value here. And when I do that, I see that it actually, it's not a very good model. We're actually really far off on the actual measured value of Phoenix. So maybe we should do this 1960 to 2000 and see what we get if we were to do that, even though I crossed it out. And it actually won't take us too long to do. So let me just show here what I would do. I'm going to go back into Edit. I'm just going to delete that first year. Okay. Now if you want, we could start this over at 0 and then go 10, 20, 30, and 40. So we're measuring off 1960. And if I did that and I calculated the exponential regression, okay, let me write that down. Okay, so this is the revised model. Let me write this in red since I crossed it out in red. The revised model, P of t, is 444 times 1.028 raised to the t. And if we want to find P of 53 in this model, so I'm going to put 53 in for t, we get 1,918.7. So that wasn't a very good model either. So neither of these are good models to predict the population of Phoenix. But we did nonetheless, and that's kind of the exercise, is how to do it, how to create this model. Alright, we're going to end this lesson with a couple of problems using the logistic growth function to model population. This one is modeling a rumor. This high school has 1,200 students, and you've got a group of students that start a rumor which spreads logistically so that this function models the number of students who have heard the rumor by the end of t days, where t equals 0 is the day the rumor begins to spread. Let me rewrite that so it's not written on here on a single line with a slash. S of t equals 1,200 1 plus 39 e raised to the negative 0.9 t. Okay, so there it is. Looks a little bit nicer now. So how many students have heard the rumor by the end of day 0? So question A is asking us to find S of 0, which is simply put, we're putting 0 in for the t in the exponent, and we're going to work that out. Now that's calculator work, so I'm going to do that on the calculator right now. And we get S of 0 is 30. 30 what? 30 students. Okay, so by the end of day 0, 30 students have heard this rumor. Now, how long does it take for 1,000 students to hear the rumor? So to do part B, we want 1,000 students to have heard the rumor. And we want to figure out what t is. How long, how many days does it take for 1,000 students to hear this rumor? Now to do this is going to be done on the graphing calculator, where we type again maybe this function into the y1 and this function into the y2, and we're going to graph them and look for where the two lines intersect each other. So it's going to look about like this. 1,200 divided by, I'm going to open parentheses, it's the e raised to the negative 0.9x. Okay, so there's the first one. The other one is 1,000. I'm going to go into my window. The x is t, and t is days. I don't know how many days. I'm just going to pick something like 10 days. And the y value is students. So I'm going to go from 0 students. The school itself has 1,200 students. So I'm going to go 1,300, just a little bigger than that. Now let's graph and see what we can see from this graph. So there's my logistic model. Remember that it does start to level off over time. And there's my line at 1,000 students. So going from 0 to 10 was just fine. I'm going to calculate that intersection point. And if we look at the x value right there, which is the t value that I want, is to be about 5.86. So the t, 5.86, and this is days. So that's how long it takes for 1,000 of the 1,200 students in this school to have heard the rumor. So near the end of the 6th day, that's when 1,000 students in this school have heard the rumor. Okay, one more problem. This one says the population of deer after T years in Cedar State Park is modeled by the function here. Question A, what was the initial population of deer? So the initial population of deer happens when time begins. So we want to find P of 0. We're going to simply put 0 in for the t in the function. And if I do that, now I'm kind of cheating. I don't really need to use the calculator, and I'll tell you why here. It's going to be 11 deer. If t is 0, then that means this becomes e raised to the 0. And e raised to the 0 power is just simply 1. Okay, so if that's 1, this is really 90 times 1, which is 90. Plus that 1 is 91. So I was able to quickly do 1,001 divided by 91. Which is not a very difficult one to evaluate there. And that's 11 deer. So that was the initial population of deer. Question 2 says, when will the number of deer be 600? So this is question B, I guess, not 2. So here we're looking for a population of 600. Now you should recognize this as one we're going to do on the graphing calculator. We're going to type in these two functions. Okay, so we've got the 1001 divided by, I'm using parentheses for the denominator, 1 plus 90 e to the negative 0.2x. And then I've got 600 in the other one. For the window, I don't really know. I'm just going to go 0 to 10, and if I need to change it, I will. For the 1300 is the maximum. I'm okay with leaving it at that for now. Let's hit graph. And so this first line in blue, this is the population of deer, and they are not growing very quickly. Okay, so don't intersect. I'm just going to check and make sure it's typed in right. And it is typed in right. So let me go back to my window and let's change this 10 maybe to 100. Oh yeah, we're definitely going to see it now. We can see how it's going to start to level off too. Okay, so we want the intersection point of these two lines. And what we want is the 24.5, the x value right there. So this happens when t is 24.5 years. So that's how long it takes for the number of deer to be 600 in the park. And part C, what is the maximum number of deer possible in the park? It'd be 1,001 deer. Remember, the numerator of this function is the limit to growth, or the maximum sustainable population. So it's simply the numerator. There's nothing else to work out there at all.